All right, let's go ahead and get started. I do want to welcome you to this worksheet. This is acids and bases. We're going to move fairly quickly through the first part of this worksheet because I want to really focus on titrations. That's the main part of this worksheet. So here we go. We're to compare the properties of acids and bases and circle any properties that they have in common. So we're going to start with taste. I want you to know that acids have a sour taste. So citrus, for example, is an acid. Bases have a bitter taste. Sodium bicarbonate or baking soda has a bitter taste. Acids, well, they just feel watery. When you put your fingers into them, they just feel like water. But bases feel slippery. Acids give off hydrogen gas, bases don't. Both are electrolytes, and acids turn blue litmus paper red, bases turn red litmus paper blue. The indicator, phenolphthalein, is colorless in an acid, but in a base turns pink. All right? So let's move on. Number 2 says this. What is the formula for the hydronium ion? It is H3O+, and how is it related to H+? It's the hydrated form of the H+. So for example, if we have an acid that produces hydrogen ions, what's going to happen is that for the most part, hydrogen ions are going to complex with water to form H3O+, the hydronium ion. Now this is an equilibrium, so there is a little arrow going the other way, but it's only a small arrow because the equilibrium lies far to the right. So H plus is really the hydronium ion of the hydrated form of the hydrogen ion is the hydronium ion. So here we go to number 3. How does a chemist define each of the following terms? A weak acid, there's little dissociation, right? That's what we mean by a weak acid. A strong acid, almost 100% dissociation. It's a strong electrolyte. C, dilute. What do we mean by dilute? So you can have a strong acid that is dilute. That means that there's little solute, lots of solvent. Or you can have a concentrated acid. That means lots of solute. That's number 3. Let's go to number 4. Number 4 says, give an example of each of the following. A weak acid. We'll use acetic acid, CH3COOH. That is acetic acid. A weak base, ammonia. NH3 is a weak base. That means it does not dissociate very readily. C, a strong acid. We'll give 2 this time. Hydrochloric acid and nitric acid. Those are both strong acids. For strong bases, we'll use sodium hydroxide and potassium hydroxide, and that'll do it for 4D. Let's look at number 5. What do we mean by neutralization? Well, when we combine an acid with a base, they form salt and water. We call that neutralization. So it's interesting to note that we've got something that has a very low pH, acid, and something that has a very high pH, a base. When we put them together, we form something that's absolutely neutral, salt and water. Salt water, in other words. All right, so here we go. Number 6. What are the products if equal amounts of acid and bases react? We've already alluded to this. It's salt and water. Salt and water are the product of acids and bases. Number 7 is an acid-base neutralization endothermic or exothermic. You should know that this releases heat. This process of acids and bases coming together to form salt and water is an exothermic process. Exothermic. Number 8, define and give 2 examples of polyprotic acids. Acids that can donate more than 1 proton. So examples would be H2SO4, that's sulfuric acid, H2CO3, that's carbonic acid, and H3PO4, that is phosphoric acid. Those are all polyprotic acids, and that'll do it for number 8. Number 9, what is a titration? The measured addition of an acid and a base to neutralize each other. So generally speaking, what a titration kind of looks like is we'll have either an acid or a base in a beaker like this, right? And the acid or the base is in the beaker. It is of unknown molarity, but we do know the volume. And then above that, we place a measured device called a burette. And the burette will drip. If this was a base in the beaker, then it'll drip as acid of a known concentration. We'll look to see exactly how much of the acid is added, and we call that a titration. So again, a titration is the measured addition of acid and base to neutralize each other. We call that device on top, but this is for number 10. What laboratory glassware is needed in the titration? We call this device that was used to drip the acid or the base into the acid or the base in the beaker a burette. So that'll do it for number 10. Number 11, what is true about the amount of hydrogen ion and OH minus concentration, or OH minus base in a solution at the equivalence point? What we mean by equivalence point in the titration is that the amount of acid and the amount of base, even more specifically than that, the amount of the number of moles of acid and the number of moles of base is exactly equal when you have titrated something, so that both acid and base are equal. That's number 11. Number 12, how can we know that the endpoint in a titration has been reached? By observing the color change of an indicator by measuring a sharp change in the pH change, as we might use, say, for example, a pH meter to measure a sharp pH change. So we either have an indicator like phenolphthalein, for example, in the reaction mixture between the acid and the base, or we'll measure with a pH probe a very sharp pH increase, or sharp, I should say, change. It could be also a decrease. Let's look at number 13. In an acid-base neutralization, the cation of the base and the anion of the acid combine to make a salt. What acid and base must have been combined to make each of the following? So here we have NaCl, right? We have sodium chloride. So what do we mix together to get that? Well, remember, we're going to need a chloride ion and we're going to need a sodium ion. So that means that we're going to have to get them from sodium hydroxide and hydrochloric acid. So the hydrogen from the hydrochloric acid and the OH minus from the sodium hydroxide are going to combine then to form the sodium chloride. All right. So when you mix hydrochloric acid with sodium chloride, you're going to get with sodium hydroxide, you're going to get sodium chloride. Let's look at this one right here. We have K3PO4. We're going to need to mix potassium hydroxide. That'll give us the potassium source, and hydrogen phosphate, or I should say phosphoric acid, H3PO4, to give us the phosphate component of the salt. So KOH and H3PO4 will do it for us. What about NH4Cl? How do we obtain this salt? We're going to need ammonium hydroxide, NH4OH, and hydrochloric acid. All right, that'll get us the NH4Cl. Potassium nitrate, we're going to need a potassium source, so it's potassium, and we're going to also need a nitrate source. So we're going to use potassium hydroxide and HNO3, nitric acid. NaSO4, that's sodium sulfate. We're going to need sodium hydroxide, sodium hydroxide for the sodium source, and H2SO4, sulfuric acid for the SO4 source. And when we combine those, we get Na2SO4. The next one is calcium nitrate. How do we get that acid? Well, let me pull this down again. There we go. We're going to use calcium hydroxide and nitric acid to do that, right? Calcium hydroxide and nitric acid will do that for us. All right, so we'll finish this up with some titration calculations. It says at the equivalence point, moles of acid in the solution is equal to moles of base. For monoprotic acids and bases, we can express this mathematically as M sub A times V sub A is equal to M sub B times V sub B. So let's look at the problem. It says for A, it says 38 milliliters of a 0.1 molar hydrochloric acid solution is needed to neutralize 25 milliliters of ammonium hydroxide. What is the molarity of the ammonium hydroxide? So again, we're going to use this formula here. The MaVA is equal to MbVB, where the A stands for acid and the B stands for base. So we'll rearrange that to give us the molarity of the base. Molarity of the base is equal to M sub A times V sub A divided by V sub B. We'll plug numbers in from the problem. So M sub A was 0.10 molar, V sub A was 38 milliliters, V sub B 25 milliliters. When we do that calculation, we get 0.5 molar ammonium hydroxide, and that'll do it for A. Let's take a look at B. B says this: 29.5 milliliters of a 0.15 molar sodium hydroxide solution neutralizes 25 milliliters of nitric acid, or HNO3. What is the molarity of the acid? Again, we'll rearrange this formula to give us M sub A is equal to M sub B times V sub B over V sub A. So we'll plug in M sub A then is equal to 0. From the problem, 0.1 molar, 0.15 molar times 29.5 milliliters divided by 25 milliliters, and we get 0.15 molar nitric acid. That'll do it for B. And finally, number C. We've got 30 milliliters of a 0.20 molar hydrochloric acid will be neutralized with 0.5 molar sodium hydroxide. What volume of the base is needed? We're going to rearrange the original equation to give us V sub B is equal to M sub A times V sub A divided by M sub B. We'll plug in. That's equal to 0.20 molar times 30 milliliters divided by 0.5 molar. Do the calculation and you will get 12 milliliters of sodium hydroxide. That'll do it for C, and that'll do it for this worksheet. I'll see you on the next one. Thanks. Bye-bye.